Hey everyone, and welcome to Calculus BC. In today's episode, we're going to be learning chapter 6.6, which is arc length, which is going to be the length of any particular function rather than the area underneath it. And so for this example, for this lesson, I'm going to start off with an example here from Desmos. If you look at this curve right here created by this function, obviously it's a curved function, but we're going to try and find the arc length from one interval to the next. And so the way I'm going to do this, the way I'm going to extrapolate the formula for arc length, is I'm going to zoom in on this curve. I'm going to zoom in on this curve really, really, really close. In fact, I'm going to get so close that the curve pretty much appears like a line, like that. And I'm going to copy that line into our program. So if I do that, that allows me to find the distance from one end of this linear, zoomed in linear thing, right? It was curved, but it is linear now, to the next. And the way I'm going to do that is I'm going to find these individual distances. So like this distance right here. And that distance will be comprised of that right triangle, and then that right triangle, and then that right triangle, and then that right triangle, and so on and so forth. Well, how much is each of these distances worth? Well, it's worth a delta z, I'll call it. So, because it's almost like the hypotenuse of a right triangle, right? This thing here is worth a delta x, and this vertical side is worth a delta y. So at minimum, what we know is we know that delta x is equal to, not delta x, delta z. Delta z is equal to delta x squared plus delta y squared, and that's underneath the square root sign. So what I'm going to do is I'm going to manipulate this thing a little bit to make it a little bit more formulaic. So what I'm going to do is I'm going to factor out a delta x. Now I know what you're thinking. How are we going to factor out a delta x squared when there's nothing to factor out of this guy? Well, there is. What I end up getting is 1 for the left term, and then delta y over delta x. And in this case, they would all be squared because they're being individually squared for the second term. And again, that's equal to delta z. Now from here, this delta x squared, I'm actually going to take the square root of him. So what I have is the square root of 1 plus delta y over delta x, all squared with a singular delta x on the outside. Now at this point in time, you might be seeing this as a bit of a familiar thing. This is derivative, right? Delta y over delta x is slope. So what we're going to do is we're going to change the slope notation a little bit. And I'm going to do 1 plus, instead of delta y over delta x, I'm going to do f prime of x sub I star. There it is, that x sub I prime, x sub I star again, and then delta x. And again, I know that delta z is equal to that. But if I make this worth the entire curve on the interval, hopefully it makes sense that I'll be doing a summation of a bunch of those delta z's. So the summation will start from from I equals 1 to n. And then I'm going to go and take the limit as n goes to infinity of that sum. And what I end up getting is the square root of 1 plus f prime of x dx. And it's the integral from a to b. And this is what arc length is equal to. Oops. Like that. So hopefully that makes sense. I'll be back in a flash with your first example. And here comes our first example. We're going to be finding the arc length of this curve here on the interval from 1 to 4. So the first thing I'm going to do is I'm going to take the derivative of it. 2/3 x to the 1/2, right? So here comes our first example here. I'm going to be taking the arc length of this curve on this interval. So the first thing I'm going to do is I'm actually going to take the derivative of this thing. I'm going to get 3/2 x to the 1/2. And if I plug it into the formula, it's going to look like the integral from 1 to 4 of the square root of 1 plus 3/2 x to the 1/2 squared dx. And if I simplify him out, I'm going to get the integral from 1 to 4, the integral from 1 to 4, sorry. 1 plus 9/4 x dx. The 1/2 and the 2 are going to cancel each other out. And now I'm going to get ready to integrate this thing. So if I was to rewrite him, it'd be the integral from 1 to 4 of 1 plus 9/4 x to the 1/2 dx. And then when I go to integrate this thing, it's a good chance for me to show you guys rule chain. It's going to be 1 plus 9/4 x to the 3 halves times 2/3, but then times 4/9 for the reversal of chain rule. And if you didn't know that, feel free to U-sub it. It's no problem. I'm going to combine like terms here, so I'm going to get 8 because 2 times 4 is 8, 27 because of the 9 times 3, and this is going to be 1 plus 9/4 x to the 3 halves power evaluated on 1 to 4. So it's just a normal integral at this point. We're going to plug in our limits of integration. So 8 over 27, 1 plus 9/4 times 4, and that's all being raised to the 3 halves power, minus 1 plus 9/4 times 1 to the 3 halves power. So these guys are going to cancel out. I'm going to end up with 10 to the 3 halves minus, if I get a common denominator, that'll be 13. So 13 over 4 to the 3 halves power. And that's all being multiplied by 8 over 27. And that is your arc length for that particular problem. Okay, I'll be back with the next example. So in this next example, I want to highlight a few issues when it comes to arc length, because while seemingly it's pretty easy, because plugging stuff in and taking derivatives of simple equations, simple functions is not that bad, I definitely want to hit some of these because some of them can get pretty bad pretty quickly. And so what does that mean exactly? I'm going to find the arc length of y equals ln of secant x on 0 to pi over 4, and it'll start off not being too bad, but I think you're going to see this, something happens with this that I don't think you're going to like. But let's go ahead and just take the derivative. Again, nothing too threatening about it. The secant x's are going to cancel. So y prime equals tan x. Nothing too crazy going on so far. I know that the length is going to be equal to the integral from 0 to pi over 4 of the square root of 1 plus f of x squared, so that's going to be tan x, so that's going to be tan x all squared dx, which will be the integral from 0 to pi over 4 of rad 1 plus tan squared x dx. It's getting a little out there, but that's okay as long as we know our trig identities. It should simplify out pretty well. 1 plus tan squared x equals secant squared x. So again, that's just going to be the integral from 0 to pi over 4 of the square root of secant squared x dx. Those guys are going to cancel. Again, it seems like things are happening and you know, some math is going on. And then we get to this step. And we start to think, wait a second, we've integrated a lot of secant squared before, but we've never actually had to integrate secant. And so this is where the problem starts to escalate and get really bad really quickly. So as part of this lesson of arc length, I'm going to show you guys how to integrate secant. And so I'm going to go and put my integral on the side here. I'm going to remove the limits of integration because it's going to require something of us that I don't think you're going to see coming. And actually, I'm going to go ahead and put the dx way out here, because what I'm going to do is I'm going to multiply the top and bottom, and there is a bottom here, it's 1. I'm going to multiply by a version of 1 that you may not see coming. And it's going to be secant x plus tan x on top and bottom. And I'm actually going to distribute the secant in, and that's going to get me the integral of secant squared x plus secant x tan x over secant x plus tan x dx. Now I'm going to give you guys a couple seconds to think about what I'm going to do next, because the next move is actually something from Calculus AB. So I'll give you guys a few seconds just to think. If you want to pause the video and think about it for a little bit, feel free to do so. Do you see it? This is a U sub problem, where U is secant x plus tan x. du is going to be, I'll go ahead and actually derive the tan x first because it's addition, so it doesn't matter. Secant squared x, and then I'll derive the secant x, which is going to be secant x tan x dx. And that right there is my linkage to become 1 over u du, which is going to become ln of the absolute value of u plus c, which is going to become ln of the absolute value of secant x plus tan x plus c. And that is going to be what I plug back into here. So every once in a while in BC, you'll see me do this, not replace the limits of integration, because sometimes it's just not really going to help me. So I'm going to go ahead and just call this ln of secant x plus tan x, and I'll evaluate that on 0 to pi over 4. So that's going to become ln of secant of pi over 4 plus tangent of pi over 4 minus ln of secant of 0 plus tan of 0. So from here, this is going to be ln of, so secant of pi over 4 is going to be rad 2, tangent of pi over 4 is going to be 1, minus, this is going to be ln of secant of 0, which is 1 plus 0. ln of 1 is 0, so it goes away, so you end up with the ln of rad 2 plus 1 as your arc length from 0 to pi over 4. So again, this is just a cautionary tale right here, that sometimes the integrals, or the arc lengths, while seemingly easy to plug in, get really bad somewhat quickly. So I'm going to come back with another example of this in a second. I'll be right back. In this next example here, I'm going to find the arc length of this function on the interval from 2 to 3. So how do I do this? Well, first of all, when I derive this thing, I am not going to be using quotient rule. That would be a terrible idea. Nothing wrong with it, but it's one of those right but crappy kind of situations. So I'm going to go ahead and see this as y equals x to the 6th over 16x squared plus 8 over 16x squared. Again, why can I do this? It's because I have a binomial over a monomial, which will then reduce into 1 over 16th x to the 4th plus 1 half x to the negative 2. This is going to help me derive faster, so I'm going to go and do that real quick. So when I derive them, I'm going to get 1/4 x cubed minus, looks like x to the negative 3. So now that I've derived him, ordinarily he would go in for the dy over dx squared, right? But that would be a terrible idea. This is really gross. So I'm going to go ahead and put him back together. So it's going to be x cubed over 4 minus 1 over x cubed. And then I'm going to get a common denominator and multiply this all back together. So hopefully you trust me. After putting it all together, you get x squared minus 4 over 4x cubed. And this is your first derivative right here. So you can already kind of see this getting kind of nasty. So let's go ahead and integrate this guy. So it's going to be integral from 2 to 3. And that's going to be the square root of 1 plus the derivative. So that's going to be x to the 6th minus 4 over 4x cubed. And that's going to be squared dx. So let's rock and roll with this thing. We have no choice but to do this. It's going to be the big hunkin' square root of 1 plus the top being squared is going to become x to the 12th minus 8x to the 6th plus 16 all over 16x to the 6th dx. Now, the way I'm going to simplify this radical, because usually the radical can have a semblance of going away, is I'm going to get a common denominator. So that's going to be 16x to the 6th over 16x to the 6th. So that's going to be the square root of 16x to the 6th minus 8x to the 6th is going to be, well, that's going to be x to the 12th plus 8x to the 6th plus 16 all over a singular 16x to the 6th. Don't forget that's dx, integral from 2 to 3. Now, believe it or not, this top expression is a perfect square trinomial of sorts, where what I'm going to get is x to the 6th plus 4 squared over 4x cubed squared. That's all underneath a radical. Dx big hunkin' integral from 2 to 3. We haven't done any calculus yet, by the way, except for maybe taking a derivative. So the square and the square root are going to cancel out. We haven't done calculus in a long time. So that's going to be x to the 6th over 4 over 4x cubed dx integral 2 to 3. Now what I'm going to do is, before I do any integration, I'm going to split this guy up again. So again, just a lot of algebraic flexibility is going to be required here. So this is going to be x to the 6th over 4x cubed plus 4 over 4x cubed dx. And that's going to get me the integral from 2 to 3 of, looks like, x cubed over 4 plus 1 over x cubed, or x to the negative 3, I'll call him, x to the negative 3, dx. Now I'm ready to integrate this dude. So what I get is looks like 1/16 x to the 4th plus x to the negative 2 over negative 2. And then, so that's going to be evaluated on the interval from 2 to 3. And now I'm going to evaluate this thing. So it's going to be 1 over 16 times 3 to the 4th plus, looks like 3 to the negative 2 over negative 2. So that's my upper limit of integration, minus my lower limit of integration is going to be 1 over 16, looks like 2 to the 4th plus 2 to the negative 2 over negative 2. And after all of that mumbo jumbo is done, and I will admit, I cheated, I put it in no calculator, it's 595 or 144. But of course, you can just stop right there. We wouldn't worry about simplifying that at all. So that is the next case of how arc length can get really bad really quickly. It starts off as a pretty benign looking problem, right? I mean, you just split it up and you derive, and then, oh my gosh, it gets really, really escalated. So it's one of those, again, algebraic warnings. Be on the lookout for arc length, because algebraically it can get kind of nasty. I'm going to come back with one more example. And in this next example here, we are going to look at y equals x to the 2/3, and we're going to evaluate its arc length on 1 to 8. So again, pretty seemingly benign arc length problem, right? So 2/3 x to the negative 1/3, okay? And we'll go ahead and plug him in. So what we've got is the integral from 1 to 8 of the square root of 1 plus the derivative squared. So 2/3 x to the negative 1/3 squared dx. And so now from here, when I square this guy, I got to be real careful here, because the 1's going to stay, the 2/3 will turn into a 4/9. But remember, when we raise power to a power, we multiply the powers together, so it'll be to the negative 2/3 power dx. We're still integrating this guy from 1 to 8. Now at this point, remember, we're going to try and get rid of this radical if we can, or try and simplify the inside as best we can here. So how do I do that? Well, I'm going to go and factor out an x to the negative 2/3 here. So x to the negative 2/3 times, what I'm going to get on the inside is I'm going to get x to the 2/3 plus 4/9. And that's all being square rooted. That's all being dxified, and that's all being on the integral from 1 to 8. So now from here, I can at least pull this guy out. So x to the negative 2/3 raised to the 1/2 power, I'm going to divide those exponents. So what I have is the integral from 1 to 8 of x to the negative 1/3 times the radical of x to the 2/3 plus 4/9 dx. Now, at this point in time, what I'm hoping you're going to see is that you see a function, and you see that function's derivative. And you guessed it, this is a u sub. So it'll be u equaling x to the 2/3 plus 4/9. du is going to be 2/3 x to the negative 1/3 dx, which means 3 over 2, right? 3 over 2 du is going to equal x to the negative 1/3 dx. At this point in time, I think it's also important that we reposition the limits of integration also. So what I've got is if I plug in an 8, this is going to be a little weird. If I plug in an 8, I'm going to get a 2, right? So the cube root of 8 is 2. 2 squared, so let's write it down here, 8 to the 2 thirds plus 4 ninths. That's going to become a 2. 2 squared is 4. 4 plus 4 ninths is 40 over 9. And then if I do a 1, right, to the 2 thirds plus 4 ninths, that's going to be, looks like a 4 over 9, so 13 over 9. So let's replace those limits of integration here. So what I've got is going to be the integral with a 3/2 on the outside of rad u du, or actually I'll call them u to the 1/2, u to the 1/2 du. My new limits of integration are from 13 over 9 to 40 over 9. So when I uproot this u to the 1/2, I'll go and switch back to white here. That's going to be u to the 3/2 times 2 thirds. But don't forget about that 3/2. That's going to stay there and cancel. Awesome. On the interval 13 over 9 to 40 over 9. So those guys are going to cancel. So what I have is u to the 3/2 on 13 over 9 to 40 over 9, which actually isn't bad of a plug-in. It's going to be 40 over 9 to the 3/2 minus 13 over 9 to the 3/2 power. And there you go. That's how you do it with that one. Now, there was another option with this the entire time. And the other option that would avert this negative exponent crisis here would have been, so you see how my original function was y equals x to the 2 thirds, right? If you ever suspect you're going to run into that situation where you're going to end up with a negative exponent, what you can do is switch forms and get y to the 3/2 equals x, and do this dy style. So now you've got x equals y to the 3/2, and what you're going to get is, if you derive, you're going to get dx over dy, and this is over x prime is going to be 3/2 y to the 1/2 power. And so now your arc length can be the integral. Now, because we switched off our limits, our arc length to be a y, to be a dy, these limits of integration 1 to 8 are no longer going to work. I got to plug in a 1 and an 8 into here. If I plug in a 1, I get 1. If I plug in an 8, I get 4. So be mindful that if you switch your limits of integration, if you switch to a dy integral, you've got to change those limits of integration. So I'm going only from 1 to 4 now. And that's going to be the square root of 1 plus 3/2 y to the 1/2 squared dy. Now, this situation should look pretty familiar because this is now the first problem, right? This is the very first example that we did, where it's from 1 to 4 of rad 1 plus 9/4 y dy. And so now with a little bit of rule chain, I can go ahead and actually call him integral from 1 to 4 of 1 plus 9/4 y to the 1/2 dy. And I'm going to get, looks like 1 plus 9/4 y to the 3/2 times 2 thirds times 4 ninths for rule chain on 1 to 4. Again, this should look somewhat familiar. 8 over 27 times, and that's going to be 1 plus 9/4 times 4 minus, I'm going to put them in parentheses here, to the 3/2, 1 plus 9/4 to the 3/2. Those guys are going to go away, and you'll end up with 8 over 27 times 10 to the 3/2 minus 13 over 4 to the 3/2 power. Now, I promise if you put these into the calculator, you will get the exact same result. I mean, you can see where the 10 comes. You can see where the 13 comes from. In this case, the 8 over 27, right? That's a result of factoring some stuff out, but you will end up getting the same thing. The 8 will jump in and interact with these guys. But if you put these into a calculator, you will definitely get the same result out. This is the introduction to arc length. And yeah, so remember, it's not really conceptually hard, but algebraically it can be a bit of a nightmare. So always be on the lookout for arc length for those algebraic things. Just because the problem seems to be going in a certain direction doesn't mean you're necessarily doing it wrong. As always, please leave questions or comments in the comments area. And congratulations on finishing Chapter 6 of Calculus BC. We will see you as we push forward towards Chapter 7 and learning new integration rules. See ya. We should just watch the